Got it. All right. Thanks, Ryan. Yeah. Hi, everyone. My name is Kata Martin. I work at Carbon Plan as a software engineer, working primarily on front end and web stuff. And I'm here to tell you a little bit about our new library or toolkit we created for visualizing Zarr data in web maps. So before I dive into exactly what that library is, I want to introduce Carbon Plan and the tools we build, describe how we used to go about building web maps and some hangups we hit there, and then describe our new approach. I'll show you a little bit about our library and step through some examples of maps we can build with this library. So yeah, who are we at Carbon Plan? We're a nonprofit group that works to ensure the scientific integrity and transparency of climate solutions through open data and tools. And what that means in practice is that we produce research and often present it through tools on the web. And because we're working in climate, we're often working with and presenting geospatial data, which means creating a lot of web maps. And by way of example, here is such a web map that we released earlier this year. Yeah, so this is a web map that's projecting risks to forest and projecting biomass through the year 2090. And we're showing 3 different risks here: fire, drought, and insects, all important when thinking about forest accounting. And we're showing these over multiple dimensions. So we're showing different warming scenarios and showing different years, through 2090. And yeah, I mean, there's a lot of data here. It's fascinating, if grim. There are a couple maybe UI and performance limitations just to touch on while I have this up. You can see that there's a bit of a jumpiness in terms of the density of the data. As I'm zooming in and out, we did not love that. And also just there's a bit of a lag, which may or may not be conveyed over Zoom when we're re-rendering the map to pull data from different years. And yeah, so to step through how we were rendering this map and why it had some of these artifacts showing up in the UI. We were rendering this map entirely using Mapbox GLJS, which is a library produced by the company Mapbox. And the Mapbox library is built by or renders vector tile and styles vector tile maps. And for us, because we work in Python, we are storing our data in Zarr. Yes, thank you, Joe, for the link. We're storing our data in Zarr. And so in order to get this data into a Mapbox map, we had to do jump through a couple hoops, namely converting Zarr to GeoJSON, and then again to vector tiles using a utility that Mapbox created called Tippecanoe. In doing so, we were representing this gridded data that we had created as collections of points each with multiple properties. So the different climate scenario and year combinations were each properties in our vector tiles. So some limitations in addition to the kind of UI breaking points that we saw, really a sticking point for us was this data generation process. And that we had to go through the process of creating GeoJSON just to get to this end state of having tiles that we could feed to Mapbox. We also had to do manual dialing to get the different coarseness of data across the different zoom levels, which is why it was jumping around a little bit. It was hard to manually dial that to be quite right. And then also on the rendering side, we're really surrendering a lot of control to Mapbox and the interfaces that they had defined for combining the different layers, styling the different layers, and just rendering and the performance there. And so in general, this approach started to feel cumbersome. We felt like we were pushing the tools to their limits with our use cases. We wanted to try something a little bit different. So kind of inspired by the fact that we were already using Zarr, and there's this nice complementary nature between tiled web maps, which is a very familiar pattern to folks who have thought about building maps on the web and that are panable, where when you pan, you're fetching new data in the form of a tile on the map, and the chunking of data in Zarr. So with that, we decided to create a library of React components, creatively called Carbon Plan Maps, we would be responsible for loading and rendering data from Zarr, synchronized with an interactive mapping layer. And yeah, so like a big distinction between the former approach, we're still using Mapbox, but really that Mapbox layer is just for kind of the panning through the world, and the actual rendering of the data is handled internally within this new library. A bit about the data before I get to a demo. We're using multi-dimensional data pyramids in a Zarr format, and we created a small library called ND Pyramid to standardize certain processing steps that we've done every time we've been creating and iterating on maps. So we're reprojecting to Web Mercator, which is very helpful for creating web maps. It works well on the web, who knew? And also we're still using Mapbox, which has like first-class support for Web Mercator. We're also using multi-scale specification to handle showing different spatial resolutions across different zoom levels, which is a pattern that we're all very familiar with using web maps. And then separately, we're processing the data using zlib compression and using 128 by 128 pixel chunking, or chunks that are 128 by 128. You can also think of them as map tiles. Kind of in my mind, they have become synonymous. Yeah, so here is an example. Lots of real-time links coming in. Here is a demo map that we created. It's up on our, I'll have links at the end, but yeah. Or maybe Jeremy will throw one in. But yeah, so here we're rendering a map. It's panable, it's zoomable. We're rendering and loading raster data from Zarr as we move through this map. And then the interaction layer is still owned by Mapbox, and the library is kind of piecing all these things together. Also, the landlines here are still being rendered by vector tiles, ultimately styled through Mapbox also. So it's really the data layer that our library is controlling. And this data set also includes multiple bands. So we can just quickly select between precipitation and temperature. And we can also scan through select a single month to look at a time. Yeah, so pretty zippy, feeling pretty good about this. Yeah, so to look under the hood a bit, the data that this library is consuming, again, is produced by the library we wrote called ND Array. And what an ND Array uses another package data tree to produce nested data where with the multi-scale data, we have separate data sets here to specify each different spatial resolutions. So a common mapping convention is that the 0th level is the most zoomed out or the coarsest data. So that's what we have here with a single 128 by 128 pixel set of data, and then so on down however many scales a data set should have. And then we have the consolidated multi-scale data here. And then just to very quickly step through what this data actually looks like. This is the actual data that we were just looking at in the map. And yeah, so here we have, this is the data set, again, produced by ND Pyramid, which has the consolidated metadata up at the top. And then if we look at into a particular Zarr group, we have a bunch of arrays and one spatial array and other arrays containing coordinates. And in the spatial array, again, we have this like coarsest, 0 in the mapping world is the coarsest level. And so we have just a single chunk of data representing the entire world's, in this case, climate average or average temperature and precipitation data. And then we have a similar story, same set of variables at all of the different zoom levels. But when we look at the spatial data, we see the higher resolution as we step through the pyramid, all the way down to this pyramid, I guess, has 5 or 6 levels. Yeah, we just see many, many more chunks for this highest resolution level. Yes, so what does rendering this look like in our library / on the browser? Yeah, so again, only the map, the like containing an interactive map piece and the like utility layers like landlines are being rendered by Mapbox GLJS. So that's over here, if we look at the component interface, that's what these map and line, these are React components. Just as a quick aside, like quick description of React, which has become my entire world. React is a pretty common library in the JavaScript and web world for creating modular components to re-render bits of UI that are reactive to props and user interactions. And yeah, so we have these map and this kind of like parent map component, which everything within it is like synchronized to the same sense of position of where am I looking at in this map and what zoom am I at and other features like that. And then the data layer, we've defined this raster component, which is responsible for reading and loading and reading the data using a small library we wrote called Zarr.js. And we're loading the data looking at entire chunks at a time, and then rendering the data from those chunks using a library called ReGL, which is a wrapper around WebGL. And we're using that to render these 2D images, basically. And yeah, so we feel like this raster component is like nearing, or yeah, semantically somewhat close to the way that we're storing the data, which is a really nice feature. When we basically like point this raster component at a source, we're consuming the metadata, that consolidated Z metadata, and using that to look at the dimensions to figure out how we're going to index into the data, and looking at the different, like to see how many groups there are, which is helpful for constructing a data structure in the browser for storing copies of the data after it's fetched. Yeah, and this selector prop is how we're doing that selecting into the data that I've mentioned. So this is, I guess, like if you're familiar with Xarray's data array selection method, this is our sort of version of that, where we're indexing into the data into an index aware way, passing like here band would be maybe that user specified either T average or precipitation value, and month, whatever month I had selected on the slider. And so we can pull just the specific data we're looking at and render that. Maybe jumping back pretty quickly. This kind of comes together the way that the different layers are pulling data and listening to my like user interactions. You can see as I'm panning and zooming through the map, we're fetching different chunks of data. So I'm at the 4th zoom level, pulling chunks of data, and pulling this gridded raster data. And then at the same time, some of these requests are failing, I guess, but we're relying on Mapbox to request the vector tile data for the landlines. Yeah, so everything's kind of moving in unison and fetching data from where it's needed. Yeah, one more example of a map. This is actually the first map we published using our new library for a research project. This is for the Climate Trace project, where we're tracking forest emissions over a 20-year period. This is kind of nice to highlight just because it feels somewhat similar to and looks a bit more similar to the other map we created, the forest risks map, using the old approach. But this is, again, using our library, reading the raster data and just styling it a bit differently. And also similarly has a time slider, and it's pretty zippy, which we're proud of, no debouncing there. Yeah. Let's see. Yeah, so a couple more kind of features of this library. We're using ReGL, and we're kind of directly accessing the GPU via shader code. And one piece of flexibility that offers us is the ability to like kind of throw whatever calculations we'd like to and perform that in the GPU. So in a highly parallelized and performant way. So this is a kind of a toy example, but interesting, or like hopefully helps explain some of the things that this unlocks. Here we're just identifying continental regions, or beginning to identify, this is not complete, continental regions using the Köppen climate classification scheme, where we're loading monthly temperature data and over a year, and comparing the lowest and highest temperature values to some constants. I mean, this could be pre-computed, but you could imagine a scenario where those constants are defined by the user. So it's good to load up that data and then look at each layer, or look at the like monthly layers individually. Yeah, so they're thinking about it in that way. There are quite a number of applications here. This is kind of more of an extension of that idea. You can also use the library to combine the data with mapped data, spatial data with user input. So an example of that would be, here we're averaging temperature data over a subset of months defined by, that I'm selecting as the user, like here, averaging over March to October. We thread my user selections through via this uniforms prop, and then we have access to those in the shader code. And you can put kind of like arbitrary user selected parameters in there. You can, yeah, you could put pretty complicated formula in here and be drawing from more dimensions than just the 12 we have here. Yeah, so kind of highly extensible. Really the main limitation that we've hit so far is that you're limited in terms of the number of spatial variables that you can look at a single time on the GPU. And so, but beyond accepting that, you can there's a lot of flexibility in terms of what you can pull from, both in the map data and in the user specified data. Yeah, so it's still pretty early days for this library. We've only published the one research project, the forest emissions project, using this library so far. We have some basic features we want to add, like validation. For example, that GPU limitation I just mentioned, like, is not explicitly validated yet. We want to add more automated testing. We want to expand our documentation. And yeah, we want to adopt this in more projects. A lot of kind of the direction of the library has been shaped by our first use cases. And so, yeah, excited to use it a bit more and figure out some next steps for it. Some of the next steps we are aware of is we want to support selections over chunks for large non-spatial dimensions, namely time has come up as one being interesting, where we can dynamically pull map or fetch map data for different time periods. And then I pointed out the selector pattern that we have in our raster component, which is right now fully baked into that raster component. We'd like to kind of abstract and standardize that pattern a bit. I think that there are opportunities to do some of that work. And also, yeah, more to do on improving and standardizing our pyramid generation. Yeah, but anyway, yeah, again, early days, very open to suggestions, feedback, contributions on GitHub, thoughts here, super welcome also. Yeah, so thank you for listening. Yeah, have a link to some of the projects here and also a blog post where a lot of this is stepped through also with some other demos.